the sun does it effortlessly. Every second, it fuses 620 million tons of hydrogen into helium, releases energy power for billions for new fuel tanks. No waste disposal problems, just hydrogen and heat. And for 70 years, we've been trying to replicate this on Earth, trying to build fusion reactors that could give us unlimited clean energy. And our dependence on fossil fuels solve the climate crisis, power civilization for millennia. And for 70 years, we've failed. Not because we don't understand the physics. We do, not because we lack the technology. We have it, but because of something Enrico Fermi identified in the 1950s. A fundamental problem. A barrier so difficult that we still haven't overcome it. And when you understand what Fermi understood, when you see why fusion is so hard, you realize it's not just an engineering challenge. It's a battle against the basic forces of nature. A fight to contain the power of stars in a machine. And that fight reveals something profound about energy, about matter, about the limits of what humans can control. Let me show you why we're still losing. Start with what fusion is. Take two hydrogen nuclei. Each is just a single proton. Bring them close together, really close, and they fuse. Become a heavier nucleus, helium, and when they fuse, they release energy. A lot of energy. More energy per reaction than fission. More than chemistry. This is what powers the sun, what powers every star. It's the process that created most of the elements in the periodic table: carbon, oxygen, iron, all. Forged in stellar cores through fusion. This is fundamental cosmic alchemy. And if we could do it on Earth, controlled and sustained, we'd have solved the energy problem forever, because hydrogen is everywhere. In water, in the oceans. Deuterium, a hydrogen isotope perfect for fusion, exists in seawater. 1 liter contains enough deuterium to provide the fusion energy equivalent of 300 liters of gasoline. The oceans contain enough deuterium to power human civilization at current consumption levels for billions of years. It's unlimited, clean. The waste products are helium and neutrons. Helium is harmless. Neutrons can be managed. No carbon emissions. No long-lived radioactive waste. No meltdown risk. Fusion is the dream energy source. And it's been 30 years away for the past 70 years. So what's the problem? Why can't we do what the sun does? Fermi identified the core issue. It's the Coulomb barrier. The electromagnetic repulsion between nuclei. Here's how it works. Protons are positively charged, and like charges repel strongly. The closer you bring 2 protons together, the stronger the repulsion. This is electromagnetism, one of the fundamental forces. And it's powerful. To overcome it, to get protons close enough to fuse, you need enormous energy. You need to slam them together at incredible speeds. How fast? Fast enough that their kinetic energy overcomes the electromagnetic repulsion, and that requires temperatures. Extreme temperatures. In the sun's core, it's about 15 million degrees Celsius. At those temperatures, hydrogen exists as plasma. Nuclei stripped of electrons, moving at tremendous speeds. And occasionally, two nuclei collide with enough energy to overcome the Coulomb barrier. They get close enough for the strong nuclear force to take over. The strong force is attractive at very short ranges. Once nuclei are close enough, it pulls them together. Fusion happens. Energy is released. But here's the problem on Earth. We can't use the sun's method. The sun achieves fusion through mass, gravitational confinement. The core of the sun is under immense pressure, about 265 billion atmospheres. That pressure forces nuclei close together, increases collision rates, compensates for the relatively low temperature. We can't create that pressure on Earth. We don't have 330,000 Earth masses to use for gravity. So we have to use a different approach. We have to make the plasma hotter, much hotter. To get fusion to occur at a rate useful for energy production, we need temperatures around 100 million degrees Celsius. 7 times hotter than the sun's core, because we don't have the pressure. We have to compensate with temperature. And this is where Fermi's insight becomes critical. At 100 million degrees, you can't use containers. There's no material that can withstand that temperature. Everything melts. Everything vaporizes instantly. So how do you contain plasma at 100 million degrees? If you're starting to realize how impossibly difficult this is, you're seeing what Fermi saw. But before we go deeper, you need to commit to understanding this. Subscribe to this channel right now. Hit that like button. Share this video with anyone who thinks fusion is just around the corner. Because what I'm about to explain will show you exactly why it's not, and why that matters. Let's continue. The answer is magnetic confinement. Plasma is ionized. The nuclei and electrons are separated. They're charged particles. And charged particles respond to magnetic fields. So you create a magnetic field, a very strong one. And you shape it so it acts like an invisible bottle. The plasma doesn't touch the walls. It's held in place by magnetic pressure. Suspended in vacuum. This is the principle behind tokamaks. Donut-shaped reactors. The plasma flows in a torus. Magnetic fields confine it. Keep it away from the walls. In theory, this works. In practice, it's phenomenally difficult because plasma is not a simple fluid. It's a gas of charged particles. And charged particles do complicated things in magnetic fields. They drift. They oscillate. They create instabilities, turbulence. The plasma wants to escape confinement. It writhes. It develops hot spots and cold spots. It generates waves that can disrupt the magnetic field. Maintaining stable confinement is like trying to hold jello with rubber bands. While the jello is boiling and electrically charged and trying to escape. Fermi understood this. He worked on fusion research in the early days, and he identified what's now called the Lawson criterion. This is the condition for net energy gain from fusion. You need 3 things simultaneously: high temperature, high density, and long confinement time. The product of density and confinement time has to exceed a certain threshold. And that threshold is high, very high. Because fusion reactions are rare, even at 100 million degrees. Most collisions don't result in fusion. The nuclei have to hit at exactly the right angle, with exactly the right energy. Most of the time, they just bounce off each other. So you need lots of collisions, which means high density. And you need to maintain these conditions long enough for enough fusion reactions to occur. Long enough that the energy released from fusion exceeds the energy you put into heat and confine the plasma. This is called break-even, and we've never achieved it. Not in 70 years of trying. The closest we've come is the joint European torus, JET. In 1997, they achieved 16 megawatts of fusion power for about 1 second, but it took 24 megawatts of input power. They got back 2/3 of what they put in. Not break-even, not even close to the goal, which is not just break-even, but ignition, self-sustaining fusion, where the energy from fusion reactions heats the plasma enough to maintain the temperature without external input. The fusion reactions become self-perpetuating. This is how stars work. Once fusion starts, it keeps itself going. We've never achieved this in a reactor. We've achieved it in hydrogen bombs. Uncontrolled fusion, but not in a controlled, sustained way. And the reason is what Fermi identified. The engineering challenges are immense. You're trying to create and maintain conditions that exist nowhere in nature except inside stars. And you're trying to do it in a machine, with electromagnets, with cooling systems, with power supplies, with diagnostics, all of which can fail, all of which add complexity. Let me give you specific numbers. To achieve fusion with deuterium and tritium, the easiest fusion reaction, you need a temperature of about 100 million Kelvin. At that temperature, the plasma has enormous thermal energy. If it touches the wall, it vaporizes the wall material. That material then contaminates the plasma, cools it, stops fusion, so the magnet no wiki spochis. No asymmetries. But creating a perfect magnetic field is impossible, because electromagnets have to be powered, and they generate heat, so they have to be cooled. With liquid helium, 2 for degrees Kelvin, for degrees above absolute zero. So you have a system where, separated by a few meters, you have plasma at 100 million degrees and superconducting magnets at 4 degrees. The temperature gradient is the most extreme in the known universe, and you have to maintain this stably for minutes, eventually hours, while extracting energy. It's absurd. It's a miracle we can do it at all. But there's another problem. Neutrons. When deuterium and tritium fuse, they produce helium and a neutron. The helium is charged. It stays in the plasma. Helps heat it good. The neutron is neutral. It doesn't respond to magnetic fields. It flies out of the plasma, hits the reactor wall. And this is where things get nasty. Neutrons damage materials. High-energy neutrons, like the ones from fusion, cause displacement damage. They knock atoms out of their lattice positions, create defects. Over time, materials become brittle, radioactive. The reactor wall becomes a radiation hazard. It has to be replaced periodically. And dealing with that contaminated material is a challenge, not as bad as fission waste, but not trivial. And this was something Fermi worried about, the materials problem. Can we build materials that can withstand decades of neutron bombardment without failing? We still don't have a definitive answer. Now let's talk about fuel. Deuterium is abundant. It's in seawater. We can extract it easily. But tritium is a problem. Tritium is radioactive. It doesn't exist in nature in significant quantities. It has a half-life of about 12 years, so we have to make it. How? By bombarding lithium with neutrons. And where do we get neutrons? From the fusion reactor itself, so the reactor has to breed its own fuel. You surround the reactor with a blanket of lithium. Fusion neutrons hit the lithium, produce tritium. You extract the tritium, feed it back into the reactor. This is called a breeding blanket, and it has to work efficiently. You have to produce at least as much tritium as you consume, ideally more, to account for losses. Building a breeding blanket that works is another enormous challenge. We've tested concepts, but we haven't demonstrated it at scale. And without it, fusion reactors can't be self-sufficient. They'll depend on external tritium sources, which don't exist in the quantities needed. We're at the halfway point, and you're starting to see the scale of the problem. This isn't just one challenge. It's dozens, each one requiring cutting-edge science and engineering. Subscribe to this channel if you want to understand the deepest challenges facing humanity. Hit that like button. Share this video, because fusion is our best hope for unlimited clean energy. And understanding why it's so hard helps us appreciate what's at stake. Let's continue. There's another approach to fusion. Inertial confinement. Instead of magnetic fields, you use inertia. Compression. You take a tiny pellet of deuterium and tritium, freeze it. Then you hit it with lasers. Powerful lasers. From all sides simultaneously, the outer layer vaporizes. explodes outward. And by Newton's third law, this creates an inward force. The pellet implodes, compresses to incredible densities. For a brief moment, the core reaches fusion conditions. Temperature and density high enough for fusion to occur. This happens in nanoseconds, trillionths of a second. Then it blows apart. But brief moment, fusion occurs. Energy is released. This is how hydrogen bombs work. The fission primer impresses secondary, inertial confinement. And we've been trying to do it in a controlled way with lasers since the 1960s. The National Ignition Facility, NIF, in California, has 192 laser beams. They deliver over 2 megajoules of energy to a target the size of a peppercorn. In a few nanoseconds. The compression is extraordinary. Densities hundreds of times greater than lead. Temperatures tens of millions of degrees. And in December 2022, they achieved something historic. They got more fusion energy out than laser energy in. 3.15 megajoules in. 3.5 megajoules, however, for the fusion reaction produced net energy. This was a breakthrough, but, and this is a big but, the lasers themselves require about 300 megajoules of electrical energy to produce those 3.15 megajoules of laser light. So the overall system is still far from break-even. You put in 300, you get out 3.5, net loss. Huge loss. And this is the challenge with inertial confinement. The efficiency is terrible. Converting electrical energy to laser energy is inefficient. Focusing all that laser energy onto a tiny target is inefficient. And you have to do it many times per second to get continuous power. NIF fires once per day. A power plant would need to fire 10 times per second, every day, for years. The engineering challenges are staggering. Fermi understood that fusion would be hard, but I don't think even he anticipated how hard. The problems are not just technical, they're fundamental. You're fighting against nature. The Coulomb barrier is not a design flaw. It's a fundamental force, electromagnetism. You can't negotiate with it. You can't engineer around it. You have to overcome it with brute force. Temperature, energy, and that requires enormous infrastructure. Tokamaks are massive. ITER, the International Thermonuclear Experimental Reactor being built in France, is the largest fusion experiment ever. It's 30 meters tall, weighs 23,000 tons. The magnets alone weigh thousands of tons. It will cost over $20 billion. And it's designed to demonstrate net energy gain. Not to be a power plant, just to prove it can be done. If it works, and that's still uncertain, it won't come online until 2035 at the earliest. And then we'll need to build a demonstration power plant, which will take another decade or two. So we're looking at 2050 or beyond before fusion could contribute meaningfully to the grid. Maybe. Now, you might ask, why bother? Fusion is this? Why nor renovables? And the answer is scale and sustainability. Fission works. We have hundreds of reactors. But fission produces long-lived radioactive waste. And it uses uranium, which is finite. Renewables are great. Solar and wind are getting cheaper and more efficient, but they're intermittent. The sun doesn't always shine. The wind doesn't always blow. You need storage, batteries, which have their own environmental costs, and raw material constraints. Fusion, if we can make it work, solves all of these problems. It's continuous, baseload power. It's clean. No carbon, minimal waste. It's safe. No chain reaction to run away, no meltdown risk, and it's unlimited. Fuel from seawater for billions of years. It's the holy grail. And that's why we keep trying, despite the difficulty, despite the cost, despite 70 years of setbacks. But Fermi would also tell you to be realistic, to not overpromise. Fusion research has suffered from hype. Every decade, there's a new breakthrough, a new design, a new promise that fusion is just around the corner. And every decade, it remains just around the corner. This has eroded credibility, made people skeptical, and rightfully so. We've been promised fusion for 70 years. Achisomi, point you have to deliver, or admit it might not be possible. Or at least, not possible on a timeline that matters for climate change. We need to decarbonize by 2050 to avoid catastrophic warming. Fusion won't be ready by then, so we can't wait for it. We have to use what we have now, renewables, fission efficiency. And we have to keep working on fusion. Because even if it's not ready for this crisis, it might be essential for the next one, for long-term sustainability, for space exploration, for a future where energy is truly abundant. Here's something most people don't realize. The difficulty of fusion is actually a safety feature. The reason fusion reactors can't melt down is because the conditions for fusion are so extreme. If anything goes wrong, the plasma cools. Fusion stops immediately. There's no chain reaction to run away. The fuel is introduced continuously. Only seconds of fuel in the reactor at any time, so if you lose confinement, you lose fusion. The reactor shuts down safely. This is fundamentally different from fission, where you have to actively control the chain reaction. And if control is lost, you can have a runaway, Chernobyl, Fukushima. Fusion doesn't have this risk. The very difficulty that makes it hard to achieve makes it safe. And that's worth something. That's a reason to pursue it, even if it's hard. Let me tell you about one more approach: fusion startups. In the last decade, dozens of private companies have raised billions to pursue fusion, different designs, different physics, different engineering, Commonwealth fusion systems, TE technologies, Helion energy, general fusion. Each claims they can achieve fusion faster and cheaper than the big government projects. Some are using new superconductors. Some are using different confinement schemes. Some are targeting different fusion reactions. Proton-boron instead of deuterium-tritium, and maybe one of them will succeed. Maybe a small, agile company will solve a problem that stumped governments for 70 years. It's possible. Innovation happens. But it's also possible they're all over-promising. That the physics fundamentals Fermi identified still apply. That there's no shortcut. No clever trick that makes fusion easy. And we'll know in the next 10 to 20 years. Either these companies will demonstrate working reactors, or they'll fail. And we'll be back to ITER and the big government programs. Fermi's answer to why fusion is hard is simple. Nature doesn't want nuclei to fuse. The electromagnetic force keeps them apart. To overcome that force, you need extreme conditions. Conditions that are difficult to create and even more difficult to maintain. And those conditions stress materials, create instabilities, require precision engineering at the limits of what's possible. This is not a problem we can solve with better software or clever algorithms. This is fundamental physics, and physics doesn't negotiate. You either meet the requirements or you don't. There's no partial credit. Either you achieve the Lawson criterion and get net energy, or you don't. And for 70 years, we haven't, not in a sustained, controlled way. We've gotten close. We've made progress. But we haven't crossed the threshold, and that's humbling. It reminds us that there are hard problems in the world. Problems that don't yield to money or effort or time. Problems that require patience, persistence, and a willingness to keep trying even when success seems distant. So what should you take away from this? First, fusion is hard because of fundamental physics. The Coulomb barrier, the Lawson criterion, These are not engineering challenges. They're nature's rules. Second, we're making progress. ITER will be a major test. NIF achieved ignition. Private companies are trying new approaches. We're learning. Third, fusion is not a near-term solution to climate change. It won't save us from the current crisis. We need other technologies now. But fourth, fusion is still worth pursuing for the long term, for sustainability, for a future where energy is abundant and clean. And fifth, understanding why fusion is hard teaches us humility, respect for the complexity of nature, appreciation for the difficulty of big problems, and patience. Because some problems take generations to solve, and that's okay, as long as we keep working. If this video gave you a deeper understanding of fusion, of the challenges, of why it matters and why it's so difficult, then you need to act. Subscribe to this channel right now. Hit that like button. Share this video with anyone who thinks fusion is simple or who's given up hope that it will ever work. Because the truth is more nuanced, more interesting, more important than either extreme. Fusion is possible. We know the physics works. Stars prove it, but it's hard. Harder than anything we've ever tried to engineer, and that makes it worth understanding, worth appreciating, worth supporting. So subscribe, share, and I'll see you in the next video, where we'll explore more of the deep challenges and profound insights at the frontier of science.